go through both my notes and some really good notes I found on the web about chapter 27, which is Gauss's law. This is a pretty complex topic. It deals with something called electric flux. To an extent, you have an advantage because we've talked about magnetic flux before. The example that I did with that, if you remember, was the bed of nails. And we looked at the total magnetic flux as the total number of nails passing through a given area. The same way, electric flux is the total summation of electric field passing through an area as well. The formula for this, and I believe it is in your chapter a couple times. I'm not sure why they have it a couple different times, but I think it's 28 point, let me check here, 18 on page 794 is the official version of this. So the thing that's interesting about this, and it comes up over and over again in the chapter, and it's kind of related to E3, which we've actually also used for thinking about rearranging that for electric field and a capacitor. The thing that's interesting about this is electric flux only depends on the charge enclosed within an area. So this Q is actually probably better to say it would be called Q enclosed. And I think as opposed to just Q. So it depends on the total amount of charge that's enclosed, depends on this vacuum permittivity, which a lot of times till now we've ignored because we think of K as the Coulomb's constant, is much easier to work with, being 9 times 10 to the 9th, as opposed to 1 over 4 pi times this constant, which is 8.85 times 10 to the negative 12th. Well, this chapter is the reason why we kind of need to know this. So essentially that is equal to the electric field strength multiplied by the area of something that's being enclosed in what's called a Gaussian surface. We are almost always going to think of that as a sphere. And that actually gets down to how we figure out electric field strength from a point source or from a circle or from a sphere, and why it's over 4 pi epsilon sub 0, because essentially that the area of something, of a sphere, is 4/3 pi r cubed. I can go through that proof or derivation a little bit later. So big idea, again, for an electric field. If it's tangent to a surface, then the flux is 0. If it's perpendicular to a surface, the flux is equal to that field strength times the area. And that's what this surface integral means. We're going to choose things where we only think about the fields that are either completely tangent or completely perpendicular. From a point source or a sphere, you can always think of the fields as coming out perpendicular to the surface. And actually for any conductor, the fields come perpendicular to the surface as well. That's because the inside of a conductor, the electric field is 0 because they cancel out. So therefore the fields must be pointing out perpendicular to the surface. So again, since we have something like this, or this for a point source or for a sphere, and the area of a sphere is 4/3 or 4 pi r squared, we can think of Gauss's law like this, since it's equal to that electric field strength times the area. That's K, Q over r squared, multiplied by the area of a sphere. And so simply the flux inside this is really equal to the charge enclosed over vacuum permittivity. So essentially a lot of this 4 pi r squared stuff cancels out both in the numerator and the denominator. So that's actually really interesting that the flux does not depend on how far you are away from the charge, only on the charge enclosed. Big idea. So example 27.2, which is on page, let me check here, probably somewhere where I'm going to have to page a bunch. Nope, page 790. Shows how we can use to find out of the flux of a cylinder of length L as well, by the way. Normally we're going to think about spheres. So, example 27.3 is used to prove the electric field relationships for a sphere. Example 27.5 and 27.3 is on page 795. Example 27.5 is on page 797. This is used to show the electric field of a long charged wire. Linear charge density, so that's charge per length. If you remember when we were looking at capacitors, we talked about area charge density as well, which is not lambda. I believe it's a weird N shape. So in this case, if you're enclosing a wire, it's got a linear charge density of something like that, lambda time, and then you multiply it by the length, that equals the total charge enclosed. So that's going to be Q times L. There's no electric flux coming through the ends, it's all coming through the wall. Well, the circumference of a circle is 2 pi r, and the area of a cylinder is 2 pi r times the length. But we know that the charge is equal to lambda times the length. So when we look at the charge divided by this is equal to E times A, the length actually cancels out as well. And so the electric field away from a cylinder only depends on how far away you are from it, as well as the linear charge density. So this was a really difficult proof in chapter 26. I think I kind of looked over it a little bit, but this is actually pretty nice. Key concept, and this is really mentioned at the end of chapter 27, really section 27.6 deals with a lot of this, and I think that's actually worth looking at. It's fairly understandable, and I think can explain quite a bit. All excess charge lies on the outside surface of a conductor. So the electric field at the surface of the conductor must be perpendicular. Why? Well, if there was any component of the electric field that was parallel to the surface, then the charges would instantly move, since electric field is equal to force divided by charge strength. So if there's any charges in an electric field that's parallel or component is parallel to the surface, they would instantly have a force on them, they'd instantly move, and they wouldn't be in an electrostatic equilibrium by definition. So pretty much if you've got a good conductor, within microseconds, the charges are at a place where they are in electrostatic equilibrium, and therefore by definition, the electric field has to point straight out. So this is a note, the charge density for a two-dimensional area on a conductor. It's often not uniform unless there's symmetry such as a sphere. So I'll go through examples with that. So finding that charge density can be difficult if we're not talking about a sphere. Special conditions, these are kind of weird. What if there's like things within a surface? Well, a Gaussian surface is something that's mentioned inside in chapter 27. I want to stress to you that it is not a real surface. It is an imaginary surface, and it's used to help us understand things. So Gauss's law in section 27.5 on page 795, there's some really good rules for that. 3 observations. 1, Gauss's law only applies to a closed surface, and that's called a Gaussian surface. 2, it's not a physical surface. It does not have to coincide with the boundary of any object, although it could. It's an imaginary mathematical surface that can help us think about charges. And we can't find the electric field, this is number 3, from Gauss's law alone. We need to apply Gauss's law in situations where, with symmetry and superposition, we can think of this shape of a field. And again, we're going to choose simple shapes such as spheres and cylinders. So let's say I choose this as my Gaussian surface. There's no charge in the hole because excess charge lies on the outside of the conductor. So there's no field in here as well. That's true of anywhere that you'd have a Gaussian surface inside the surface of the conductor. So this leads to the idea of electromagnetic screening, or a Faraday cage, which is pretty cool. It's a Faraday cage is basically something shown in figure 27.32 on page 800. I'll try to upload a video about that also, kind of a southern redneck video about how they could use Faraday cages and giant Van de Graaff generators. So this is also brought up in the final chapter we're going to look at. So what about a charge inside a neutral conductor? So let's say that we've got charge here that's a net positive charge. These diagonal lines are showing empty space. And this area here is a neutral conductor. So it has no net charge on it. So if you notice, I've got 6 positives on the outside, but there's 6 negatives on the inside surface of this. Why are the negative charges on the inside surface? Well, it's because with these 6 charges here that are positive, and by definition within a conductor, the electric field has to be 0, these negatives are drawn to the inside surface. So anywhere in between here, there's, including this blue line, there's no net charge enclosed and there's no electric flux. If we had a different line, something like, say, okay, I'm going to have to fix that. Let's make it pink. If I now had this, gotta make it a little smaller, is my Gaussian surface, this pink line, there would be a net flux in here because it's only containing those positive charges. But within this conductor itself, there can't be any flux, and there can't be any charge enclosed. Okay, so there's a net, if this has a net charge of plus Q, there's a net charge of minus Q on the inside surface and a net charge of plus Q on the outside surface. So essentially, the charge of plus Q in the hole polarizes this conductor. Now, if an object's not a conductor, like say a solid plastic sphere, and the charge could be spread uniformly throughout, meaning throughout the entire plastic sphere, inside, outside surface, all the way through, then there's some other things that go on here. We can use Gauss's law for this, but we need to find the amount of charge enclosed in the field based on the sphere's volume and charge density. I'm going to do one example with that. I'm going to ask you to try one of those as a homework problem as well. Example 27.4, which is on page 796 and 797, illustrates this. The diagram 27.25 does a really nice job, and I'm going to try to explain that as well. That's actually very analogous to a gravitational field with the Earth, where we would assume that the mass would be uniformly throughout the sphere of the Earth. That's a little bit of a lie because the Earth's density is greater toward the center. And I usually do an example of that in class for us to think about it. So here's a couple sample problems from the back of the book, different than ones which I'm assigning you. Problem 7, a cube contains negative charge. Determine the missing field on the front face of the box to find the minimum field strength. So this is supposed to show 20, I assume, units coming out, 10 units coming out, 10 units coming out. So that's 40 units going out. There's 20 and 15 going in. That's 35 going in. So we need at least 5 more units going in, entering the box in order to have a negative charge inside. Because flux points towards, you have a negative flux when you have a negative charge enclosed, positive flux when you have positive charge enclosed. Problem 39, a 20 centimeter radius ball is uniformly charged to 80 nanocoulombs. What's the volume charge density? So I think that's that weird N symbol, and I can't do that on this page. But basically, I've got that amount of charge, 4/3 pi r cubed is the volume. So the volume charge density is 2.39 times 10⁻⁶ coulombs per cubic meter. So if we find the volumes of the spheres for 5 and 10 centimeters and multiply those by the charge density, we can find the field enclosed at 5 and 10 centimeters. For 20 centimeters from the center, it's just enclosing all the charge, which we've told you is 80 nanocoulombs. So here, the volume of a 5 centimeter radius, the volume of a 10 centimeter radius, multiplied by the charge density, would give us this at 5 centimeters, and this at 10 centimeters. So notice what happens. Each time the radius is doubled, the volume increases by a factor of 8 because it's cubed, 4/3 pi r cubed. The charge is going to increase also by a factor of 8. So we go from 1.25 times 10 to the 9th to 1 times 10 to the 8th to down here 8 times 10 to the negative 8th. I guess those are all negative exponents. So to find the flux, that would just be the amount that's enclosed within that area. So over vacuum permittivity, and since I have those charges, vacuum permittivity, and that equals electric field strength times the surface area at those distances as well, I could rearrange that to solve for field strength. 4,500, 9,000, 18,000. So notice the field strength doubles as the radius doubles, even though the charge is increasing basically by a factor of 8. Well, why is that? Well, the big idea is if you're doubling the radius, since the volume is cubed, you're increasing the amount of charge enclosed by a factor of 8. But if you look at the surface area of a sphere, which is 4 pi r squared, the surface area is increasing by a factor of 4. So charge enclosing increasing by a factor of 8, surface area increasing by a factor of 4. So therefore the field strength would be getting stronger and stronger as long as you are still enclosing more and more charge. So field strength doubles as you double the distance out. Like I said, I think this relates really well to this example. All right, so that's part one, my notes. I'm going to stop now for a second and get a glass of water.